Here we have the ordinary differential equation, x times the common logarithm of x dy plus the square root of the quantity 1 plus y squared dx is equal to 0. The first thing we should notice is that the x's are associated with dy and the y is associated with dx. This implies that we have a separable differential equation. The first thing I'll do is move the dy expression over to the right hand side, and this will yield the square root of the quantity 1 plus y squared dx is equal to negative x times the common logarithm of x dy. We can now separate our variables through division, and this yields dx over negative x log x is equal to dy over the square root of the quantity 1 plus y squared. We have separated our variables. All the x's are on the left-hand side, all the y's are on the right-hand side. Thus this is indeed a separable differential equation. And now we can anti-differentiate. But also, let's notice one important thing on the left-hand side. We have this negative x log x. It's on the denominator. We don't want that to be 0. When would that be 0? When x is 1, because the logarithm of 1 is 0. So note, x cannot equal 1. And this note will come in handy later on. But now the question is, what does this left-hand side equal? Can we do a u substitution? Notice that the logarithm of x, if we take the derivative, we would get 1 over x, and 1 over x does appear in this expression. Hence it would be a good u substitution. We'll stipulate that u is equal to the common logarithm of x. If we take the derivative, we get du is equal to 1 over x dx, or in other words, dx over x. And now let's use this information to rewrite our expression. Right now we just have dx over negative x times u, where u is a logarithm of x. Du happens to be dx over x, and that appears in the expression. And so we can substitute that du in. So this gives us minus indefinite integral du over u, and that equals negative natural logarithm of the absolute value of u. But u happens to be the logarithm of x, and so this gives us negative natural logarithm of the absolute value of log x. So this is the left-hand side. But let's note something. Technically, we really should put an absolute value sign with this x, because x cannot be 0. So x must be greater than 0. What about the right-hand side? We can't do a u substitution here. For example, the derivative of y squared is just 2y. That appears nowhere in the expression. We can't say u is equal to the square root of the quantity 1 plus y squared. However, this expression looks a lot like something you would find in trigonometry, so a trigonometric substitution will be helpful. Consider the right triangle. So here's the right angle, here's angle theta. If we set the hypotenuse to the square root of the quantity 1 plus y squared, and have this side y and this side 1, we have a good right triangle. Think about the Pythagorean theorem. For example, if we were only given this side y and this side 1, and we had to solve for the hypotenuse, we would get this expression, the square root of the quantity 1 plus y squared. So it's good. And let's also note, because this is a trigonometric substitution, so katoa, cosecant, secant, cotangent. To this day, I still write that down. All right. What should we do? Well, note that y is equal to the tangent of theta. So here is theta. So theta, of course, if we take the tangent of theta, we get the opposite over adjacent, so that's just y. So this looks like a good substitution. And what's the derivative of that? It would be dy is equal to the secant squared of theta d theta. And now let's use this information to rewrite our integral. We have dy, which is the secant square root of theta d theta over the square root of 1 plus y squared, which is the tangent square root of theta. But we can further simplify this. Let's think about this 1 plus the tangent square root of theta. We know our trig identities, that sine square root of theta plus cosine square root of theta is equal to 1. That just comes from the Pythagorean theorem. If we divide everything by cosine square root of theta, we get tangent square root of theta plus 1 is equal to the secant square root of theta. And we have 1 plus the tangent square root of theta, and that's just the secant square root of theta. So let's just simplify this expression here. We have the square root of the secant square root of theta, but that's just the secant of theta. So we have the integral, the secant square root of theta d theta over the secant of theta, and that just simplifies to the indefinite integral, the secant of theta d theta. Then what is this? Well, that's just the natural logarithm of the absolute value of the secant of theta plus the tangent of theta. We're in this trigonometric world. We want to return to our y land, so to speak. But what's secant of theta? If we look at our right triangle, we see that the secant, of course, is the hypotenuse over adjacent, so that's just the square root of the quantity 1 plus y squared. So we'll get the natural logarithm of the absolute value of the quantity square root of the quantity 1 plus y squared. And then what is tangent of theta? So we have our theta. Tangent is opposite over adjacent, so that's just y. So this is plus y. And this is our right-hand side. And let's put this together. So we have minus natural logarithm of the absolute value of log, the absolute value of x, is equal to the natural logarithm of the absolute value of the square root 1 plus y squared, then plus y, and I will add an arbitrary constant, which I will call c0. Alright, we can simplify. The first thing I'm going to do, just because, at least in my mind, it's easier, maybe not that much, but I'm just going to times everything by minus 1. And then we get this expression. C0 technically changes, so I could rewrite that. I'll just say this is C0 tilde. But I really don't have to, because it is, after all, an arbitrary constant. Right now, we have to keep in mind our various properties of logarithms. Okay, so we can rewrite this expression. For instance, recall that if we have the natural logarithm of x, this is the same thing as log base e of x, and let's just stipulate that equals y. We can rewrite this as e to the y power is equal to x. So with this, we can take this expression and rewrite it. We can say that we have e to the power of minus natural logarithm of the absolute value of square root of 1 plus y squared plus y, and then we have this plus c0 tilde, and that is equal to the absolute value of log absolute value x plus, oh, no plus there, okay. Alright, so we've simplified that, but we can do some more simplification. Note that if we take this minus sign, we could apply it to this expression in here and put it to the minus 1 power. Okay. In other words, we would get e to the natural logarithm of the absolute value of 1 over the square root of 1 plus y squared plus y. Also, note that we have this c naught tilde. Okay, so this brings to mind another property of exponents. For example, if we have e to the x power times e to the y power, that's just e to the x plus y power. And so we can say this is times e to the c naught tilde power. And then we have the right-hand side remaining the same. All right. Note another thing. Logarithms and exponents with the same base cancel each other, because we have this e raised to the natural logarithm of such and such. Those cancel. Or in other words, we can think of it this way. If we have b to the log base b of x, this would just be x. And so we can write, we have the absolute value of the following quantity. And this e raised to the c naught tilde power is an arbitrary constant, so I'll just say that's c, and that equals the following. All right, let's deal with these absolute value signs. Can we do anything here? Can we simplify? If we consider this expression right here, what is the range? Can we ever get a negative answer? The answer is no. It's always going to be positive, so we can drop the absolute value signs. So now we have c over the square root of the quantity 1 plus y squared plus y. And now we have a lot of absolute value signs here. Can we drop these? Well, we actually can. We can do a plus and minus. But c, if we say c plus and minus c, and c is an arbitrary constant, there's a sense in which we can just say this is equal to c, because this plus and minus absorbs into that arbitrary constant. Thus I can say this is just equal to the logarithm of the absolute value of x. Alright, so now we're almost done. We could simplify a little more, I suppose. We can just say this is c is equal to the common logarithm of the absolute value of x times the quantity, the square root of the quantity 1 plus y squared plus y. And this is a good answer, but remember, x cannot equal 0. That's no good. The log of 0, we don't want that. But also remember, in the beginning I said x cannot equal 1. So here is our final answer. Pretty neat. So c is equal to log absolute value of x times the quantity, the square root of 1 plus y squared plus y. X cannot equal 0, x cannot equal 1.